about electrical meters. Okay, now that we're fairly familiar with them, hopefully. So, if we have an ammeter, what does an ammeter measure? Current. Okay. Where should you put an ammeter in the circuit? What should it be, in series or should it be in parallel? Always series, okay? Because, so ammeters must be connected in series. What kind of resistance does an ideal ammeter have? Zero, okay? Which means if you put it in parallel, what does the current do? Yeah, if you put it in parallel with this resistor, right, it's all the current's going to go through the ammeter. Well, that changes the way that the circuit functions because you've essentially gotten rid of one of the resistors, and what you measure, although you will get a current, is not representative of what you're trying to measure. Okay, so what you have to do when you're measuring current is you have to force the current to go through the ammeter. Since it doesn't have a resistance, it's not going to change the equivalent resistance of the circuit, and therefore it won't change the current. Okay? How about voltmeters? Where do we put those? Yeah, those go in parallel. What kind of resistance does a voltmeter have, an ideal one? What's the opposite of zero? Infinity. Okay? Because what you want when you connect the voltmeter is to not change the function of the circuit. So if you put a really large resistor in parallel with some smaller resistor, where does the current go? It stays going through the smaller resistor, and almost no current flows through this. Okay? Because if any current flows through this, it changes the equivalent resistance of the circuit, and then your measurement's wrong. Okay? So a voltmeter has infinite resistance, physics infinite, which is like, yeah, it's close enough. And then an ammeter has approximately zero resistance. Okay, so very low resistance for measuring current, very high resistance for measuring voltage, which is why you have to switch the dial back and forth so it knows what you're doing. Okay. It's also why you have to change where the cords go, because you're actually changing the internal resistance of the meter. All right? So here's some household electrical safety. You won't be tested on this on the test, but you may be tested on this in life. Yeah, or death. In which case you failed. So here's sort of the diagram of a circuit diagram of what your household electrical system looks like. So here's your power coming in from your power company. Here's your meter. This is a main fuse, okay? Then you have all these other fuses. So remember, how many of you have been outside to look at your fuse box or to your closet?
It's not really a fuse anymore.
What?
Breakers.
Okay, breakers.
But our fuses are kind of old.
It's like right? They serve the same function. And what's the function of the fuses or breakers?
To lure you to the basement.
To lure you to the basement. Sorry.
If it overloads, it'll trip.
Yeah.
Or in the fuse case, it'll break.
And what are we trying to prevent?
The continuous surge.
More than a certain amount of current, because each wire that you have in your house is rated for a certain maximum current. Yeah. Okay? What happens if you go over that maximum current?
It'll trip.
Yeah, it's going to get hot, right? Because remember, wires, even though we idealize them to have zero resistance, actually do have resistance, and it depends on their cross-sectional area and their length, right? So that's why we have bigger wires for carrying power around the neighborhood, and bigger wires, like fatter wires, for carrying power into your house, and then thinner wires for just going to lamps and things, okay? That's because if they're carrying a lot of current, right, we know the resistance of the wire is the resistivity, so that's like the material property, so let's say they're copper, okay? The length divided by the cross-sectional area. So if we want to have less resistance, we need bigger cross-sectional area if we're going to have a large current, okay? Most wires are rated for about 20 amps. Once they get more current than that, for household wiring, they get really hot and either start a fire or melt, okay? Both of which are bad. So we have all of these breakers or fuses set up to stop power stop the flow of current if they reach 20 amps. Okay? So anyway, what do you notice about all of the things in your house? Are they in series or parallel?
Parallel.
And they're in parallel. Although, if you look at these individual things, these are kind of in series, okay? So the load for each individual outlet, when you're plugging a bunch of stuff into an outlet using an extension cord or some sort of power strip, you're changing that a little bit because that can be in series. Depends on how you set it up. But you usually have a hot line and a neutral line. They're supposed to have standard colors, but it depends
black,
on how
white.
good of an electrician you have. Yeah, they should be black and white. Which one's which?
White is neutral, black is hot.
Yeah, white, neutral, black, hot. But sometimes, depending on, you should be careful. Always take a voltmeter.
Well, as of like, I don't know, like 20 years ago, it's all been standardized across California.
Yeah, but I found that like when you...
Like if you go to older houses, it's a little bit different.
It depends on if you hire like a licensed electrician or you're like some guy named Steve like did the wiring himself. Like the last person that lived there and like was like, this wire works.
Like, did he get individual rolls of wire?
Yes.
I'm
just saying, I have several friends who've like gone and like tried to redo the electrical work in their house, and it's like just random hodgepodge of colors. So it's standard, but you know, I'll still be careful. Yeah. So the neutral line is connected to ground, okay, and the hot line is connected to the power coming into the house. All right. Now, ordinary lighting and outlet wiring in-house uses 12-gauge wire that has a diameter of about 2 millimeters, 2.05 millimeters. It can carry a maximum current of 20 amps safely. That's why we talk about these breakers going off at about 20 amps, okay? And that's standard. Household wire, pretty much always 12-gauge. We use larger diameter wires for to get lower resistance. So 8-gauge is about 3 1/4 in diameter, millimeters, okay? 6-gauge is about 4.11 millimeters in diameter. All right, so remember, as gauge goes down, diameter goes up, which is confusing, but you just have to remember. And so those are used for high current appliances. So 6 and 8-gauge wire. What's a high current appliance you can think of? Dryers, okay, yeah, and maybe fridges. So, yeah, and then 2-gauge or larger, right? So 2-gauge is like 6.5 millimeters in diameter. So like, something like that. That's what's coming into your house from the outside. Okay. So remember, as gauge goes down, diameter goes up. All right. Household circuits. Here's a diagram of a circuit breaker. Here's your live line. Here's your neutral line. It runs through your meter. If you have solar, up until recently, I think they're about to change it. They have something called net metering. Okay. Which means any of the solar power that you generate that you don't use goes back to the grid, and it just runs the meter backwards. Okay.
So it's free for the city.
But it works differently now.
Yeah, no, they
'Cause it's,
changed the regulation.
The way it works is you don't even use any of the electricity you generate for your solar powers. It goes straight to your grid, and that gets like indicated by the box they install.
Yeah.
And then they just charge you or give you money at the end of the year.
Yeah.
Depending on how much you generate during the year.
So this is an interesting
that's the thing,
that
they give you
happened.
money
So
for it.
yeah, this is
Yeah.
a very interesting thing that happened. So when very few people had solar power, the utility was like, whatever, like this isn't going to make a big difference to our bottom line, and so they were just running it through the same meter. So it would, if you were using power, it came in. If you weren't using the power, it went out. Okay, and they called that net metering. Now the problem with that is the way that we have a flat rate of like the cost of energy that we pay. Well, a tiered rate, okay? But that's based on a calculation that the utility does where they figure out what the costs are, because the cost of energy on the grid changes, I think, every 2 or 5 minutes. Okay, so there's like a market where all of the utilities and the power exchanges buy and sell energy, and they allocate it differently on the grid, okay? And this is based on like power use, what power plants they have running and other conditions. But since it changes regularly, they don't do that to consumers. They just sort of average it, and then they throw on like an overhead cost of running the utility, and that's what we pay for, Okay? When you're net metering, though, the problem is a lot of the time when we have an excess of solar power, a lot of it doesn't get used because you'll get it during the day when it's sunny, and unless there's a lot of people running their air conditioners, like in winter, for instance, that power should be relatively cheap because that's not a time of the day where we're going to need a lot of power. So you could be getting paid out much better rates than the utility is making for that power. And that's why net metering doesn't really work when a lot of people have solar panels. Yeah, that's why they changed it. So I'm just telling you the history of how we used to.
No, I was just saying, like, I didn't know why they were doing it. I don't know if I was getting ripped off or not, but now I know.
The reality was when we did net metering, anybody who was selling solar energy back to the grid was making a killing because that wasn't the rate that it was worth. You were getting the consumer rate, which is awesome and encouraged a lot of people to get solar power, but isn't like realistic once we scale up. So yeah, now
those people are getting ripped off.
Well, now it's more fair, but it sucks if you were trying to like beat the system because you can't anymore. Okay. Anyway, fuses, like you said, fuses, older breakers, newer. You should not have fuses in your house anymore. Although fuses do show up in things like some of the what? Cabins?
Yeah, cabins.
Well, in cars too, right? We have fuses in cars, don't we? Still have. There's fuses in the electric meters, right? There's fuses in a lot of our power supplies. So a fuse is really the reason we used to have fuses. Fuses are really simple. Okay, a fuse, excess current. Basically, you can see this is a conductor. This is a conductor. There's a wire that goes between it. If this is set up with like some sort of alloy that melts when you get to a certain current. So it melts before your actual wire melts and it breaks the connection. Okay? The circuit breaker is just a switch. So it once you reach a certain current, it flips the switch and you can flip it back. Which, if you haven't fixed the problem, might just result in it flipping again. But at least you know. Okay? This is sort of the difference between the 2 and 3-prong plug, okay? So, you know, like when you look at the wall, these all have 3 prongs. Most older houses have the 2-prong system. Both of them you have grounding. It's not like they both use grounding. There's a subtle difference here, okay? Here you have a hot line and a neutral line, right? So it comes in, goes out. If something breaks inside your appliance or device that you have plugged in, and the casing is made of metal, you can get electrocuted because the casing isn't grounded. Okay? If you also ground the casing, it's a little bit safer because if something breaks inside the circuit and touches the metal casing, then it doesn't electrify it. Okay? So 3-prong a little bit safer than 2-prong if you don't like being electrocuted. Okay? All right. We have this last problem. Which I think let's just.
So here we have a household circuit, and what we know about all household circuits and pretty much all car circuits is that they're always in parallel. So we have a 120 volt source, and it's actually AC, which we haven't talked about, but this is a pretty good approximation. It's connected to a toaster, an electric frying pan, or like a griddle, and a 100-watt lamp. So we'll call this toaster, fry pan, lamp. And we know that we're given the power of these things. This is a 120 volt, and this sort of tells you the voltage. So this is our 120 volt circuit. It's got a 20 amp max. And we want to know the current drawn by each device and the resistance of each device. And then we want to know, is this going to trip the circuit breaker? So the first thing we're going to do is figure out the current and resistance for everything, and then finally we're going to add up all of the currents and see if they add up to more than 20, because that 20 amp, that's the maximum current. Okay, so we're going to start by figuring out the formulas. So we know that power is equal to current times change in voltage. So that means we can rewrite this as current is equal to power divided by change in voltage. All right, so here's our lamp. We'll do this for the toaster. So let's say, oh, and then for resistance, we know that power is equal to delta V squared over R. So that means we can say the resistance is equal to delta V squared over P. So we can do this as a little chart where we have toaster, fry pan, and toaster, fry pan, and lamp. Then we have current and resistance. So for each of these, the current is just going to be, let me move this over. The current is just going to be the power over the voltage. So that's, for a toaster, 1800 watts divided by 120 volts. That's 15 amps. For the fry pan, that's 1300 watts divided by 120 volts. That's going to be 11 amps. And for the lamp, that's going to be 100 watts over 120 volts. That's going to be 0.83 amps. So 15, 11 amps, and 0.83 amps. And then for the resistances, for the toaster, that's going to be 120 volts squared over 1800 watts. That is 8 ohms. Then we have frying pan, which is 120 volts squared over 1300 watts, which is 11 ohms. And then resistance of the lamp, which is 120 volts squared over 100 watts, and that's going to give us 144 ohms. So 11 ohms, 144 ohms. Here's our chart. And you can see when you add up all of our currents, we're done with part A, you're going to get 27 approximately amps. Well, this is much greater than 20 amps, so we trip the breaker. All right, and it turns out household circuits really are just this simple. All right,